I'm really excited about today's video. Well, I'm excited about them all really, but today I've had to learn something new. I've had to see things in a slightly different way. So I'm excited because I'm learning something. Normally I'm talking about things that I've talked about a lot before, and this time I'm talking about something I've just learnt and I'm excited to show you. So today I want to talk about complexity. Or perhaps another word for this is chaos. Chaos theory, complexity theory, sometimes used interchangeably, but what I want to show you today, what I want to talk about today, is sometimes called the chaos game. And let me take a step back for a minute. I want to start with some words from Robert Cowan. Robert Cowan wrote a chapter in a book on education, an edited volume. The title was Learning from Comparing, and Robert Cowan wrote a chapter called Late Modernity and the Rules of Chaos. And that strikes me as extremely profound. I mean, I'm not saying that Cowan would have agreed with me, but I find them profound because I interpret those words in a particular way. The rules of chaos. If you think about chaos, normally you think about disorder, you think about disorganization, lack of predictability. And what I think is serious about complexity theory, what's serious about chaos theory, is if you look beyond the confusion, if you look beyond the chaos, there are rules. There are rules and patterns of behaviour, and what I'm going to do is try and show you something of that today. And first of all, I want to say this is the game of chaos. Here's what's going to happen. We're going to draw 3 dots, more or less, a triangle. Equilateral triangle doesn't need to be, but that's what I'm going to try and demonstrate. And we're going to pick a point, anywhere a point, like that. And what I'm going to do is I'm going to roll a dice, 6-sided dice. I'm going to choose at random one of these points of my triangle. Let's suppose that if we roll a 1 or a 2, we go towards that one. If we roll a 3 or 4, we go towards that one. And if we roll a 5 or a 6, we go towards that one. Let's suppose we roll the dice, comes up a 2. What happens then is we're going to move towards this point halfway. The point we started from, move halfway to that point. If we move again, if we roll the dice again, this time if it's a 5, we go halfway towards this point. That's about halfway. And we start drawing in dots like that. Throw a 3 halfway. Now what would happen, it's taking me a long time drawing these dots, what would happen if I could get a computer program set up so that it developed those points for me automatically? I'm going to show you now a computer program drawing in those dots to speed up, and what you'll see happening is, I think, is quite extraordinary. If you've never seen this before, watch carefully as the pattern emerges now. And you can see that the pattern is taking shape in front of your eyes. That simple rule, moving halfway towards one of the corners of the triangle, produces this beautiful pattern. It's called the Sierpinski triangle or the Sierpinski gasket, and it's a fractal. The the little triangles have little triangles inside them, and the little triangles have little triangles inside those, and each one is self-similar, and they go on infinitely smaller and smaller and smaller. And isn't it remarkable that that simple rule of drawing dots, it's unbelievable. Frankly, it's surprising, isn't it? Why is there that space in the middle that never gets filled in? Why is it that space, no dot ever accidentally lands in that space? Well, I'm going to try and explain to you why it is that no dot ever lands in that space. Each dot, every time you, here's the explanation. Each dot, every time you roll the dice, moves halfway towards one of the points at random, and that produces this pattern. Did that help? Did that help explain why it's like that? No, of course it didn't. Because if you want to understand the pattern, you have to understand the pattern. It's no good looking to the dots to explain the pattern. Let me explain again what I mean. Let me go back to the board and let's have a look at that triangle. And this time I'm going to say, imagine that's the whole pattern. That's the triangle is the whole pattern. And I'm going to ask you to compress it down into this corner. Instead of having big triangle, I'm going to make a triangle half the size, and I'm going to squeeze it down here in this corner. Now, of course, one of the effects of squeezing that triangle down to half its size over in this corner is that every point in the triangle will move halfway towards that corner. You can see there's a connection between the instruction that we gave the computer to move the point halfway towards this corner and the fact that we're compressing the whole pattern down, moving down. They move together, all of the points move together halfway towards that corner. Let's suppose we throw the dice and it points this corner. Let's take the whole pattern and let's compress it down into that corner. And again, when we compress it down, every point in the pattern moves halfway towards the corner. From where it was, the point that was here moves halfway towards the corner. The point that was here, halfway towards the corner. Every point in the pattern moves halfway towards the corner. That was how we constructed it, was by drawing dots that were moving halfway towards the corner. Or imagine we took the whole pattern and we squeezed it up into this top triangle, half the size, move everything halfway towards the top corner. And you can see that on each dot that we put in, we're moving the whole pattern halfway towards the corner. And now it's obvious. It's not just an accident. It's necessary that that middle part is left blank, because what we're doing is contracting the whole pattern down, whole pattern down, whole pattern up. We're squeezing the whole pattern into a half of its space. And that space in the middle is always left blank. Now you understand why that middle triangle has to be left blank, and you don't understand it by studying the dots that make up the pattern. And this is something that's very special about complexity, is there are different levels of organisation, and in order to understand one level, you don't have to look below at a lower level. Now that's not often in life, that's not a normal procedure. If something breaks, normally speaking, if my fridge stops working, I go looking for which bit of the wiring has become disconnected. I can understand a system by looking at its parts, but in complexity, telling you about what the dots were doing didn't help you understand what the pattern was doing. If you want to understand the pattern, you have to think pattern level. If you want to understand the dots, you have to think dot level. It's a quality of complexity that is called emergence. The overall pattern is one level, the dots are a different level, and although they're obviously connected, there's not a direct and obvious connection between. To understand the pattern, you don't need to understand the dots. And understanding the dots won't necessarily help you understand the pattern. So complexity doesn't work like many of the things that we experience in ordinary life. Well, except a lot of the things that we experience are ordinary life. And think about how often in education we're looking at a system problem and we start asking about what individuals are doing. People will talk about whole school culture. Who has a role in shaping whole school culture? Is it the head teacher? If it's the whole school culture, it's the whole school culture and the whole school is responsible for it. There's no point in looking for the problem lower levels down. See a problem with international students adjusting to their host society? What do? We go and interview individuals and ask them what's happening. That's completely wrong. If it's a problem that's systemic, that's at pattern level, then we have to look at patterns. So what I want to impress upon you is this quite magical emergence of patterns from seemingly simple organisations like the game Chaos Game. It illustrates emergence. It illustrates that you can't necessarily understand the pattern by understanding what makes up the pattern. If you want to understand the pattern, you need to think at pattern level. And emergence is something I'm going to have more to say about, because I think that it's an issue that's important in education and in how we study education. But the other question is, how can we study more fully complexity? And it takes me, you've just seen a very simple computer simulation of a complex system, drawing in the dots, drawing in thousands of dots to make up the pattern. And we can run that because it's a computer program. We can run it again and again and again, and we can see the patterns that emerge. And that takes us in a different direction for computer simulations of what are called agent-based models. So this is the lesson for today. Complexity, patterns, there are rules in the chaos. It's just as Robert Cowan said, what we need to understand in situations, he was pointing at situations of great social turbulence. In situations of great social turbulence, we need to understand the patterns that are emerging, the rules that are hidden behind the chaos, beyond the chaos. We need to think beyond simply it's disorganized, it's unpredictable. We need to be looking towards a deeper understanding of the rules that govern chaos, the things that can be done, but quite importantly, the things that can't be done. The dots don't go to these places. There's a clear restriction on where the dots go, and they don't go to the middle of these triangles. So there's rules that are coming out of the emerging from the complexity. And that's what I want to draw your attention to, and we're going to have a look at agent-based modelling as a way of understanding that, computer modelling. In another video I'll look at agent-based modelling, and in another video I'm going to look at emergence in slightly more detail.